this FGX is. Let me grab my calculator. I just thought today we could benefit from working through a problem together. In review, what I did to solve this problem number 1 is I drew a free body diagram, because my free body diagram is going to help me visualize these relationships. And important in these relationships is the fact that the mg cosine theta is a vector that goes that way. My mg sine theta is a vector that goes down the ramp. And the normal force goes up and the force of friction goes that way. Sure, that's cool. That's cool to keep in mind. And keeping the references in mind are important as well. You know, if I were to throw these on here, I would say force of friction this way, balanced out with mg sine theta this way. And then I would say normal force that way, balanced out with mg cosine theta this way. Those are the vectors that are in the proper dimension of x and the proper dimension of y going this way. How does that help us? Well, it helps us with question A because it eliminates the normal force as something that doesn't work down the ramp. And for B, it talks about the role that the gravitational force does in pulling this down the ramp. Because work is force times displacement, if I'm looking at B, this is literally all I have to look at for B. For B, I only have to think about the force as it's moving from there to there. And since the force is lined up with the displacement vector, we know this is going to be a positive work done. All I need is my mg cosine theta, so that's going to be mg cosine theta is going to be 4 kilograms times 9.8. But I got to multiply it by sine theta. Sine of 30 degrees is, this is in radians, so that's not good. Hang on a second. Sorry, my daughter was clocking out some radians on here apparently. 0.5. There. And then we'll multiply that by our 5 meters. I put it in here. This is 100 joules. 100 joules. So the work done by gravity, moving it from here to here, a position of 0 at the top of the ramp, and then we're looking at 5 meters right here. So this is literally a change of x equals 5 meters right in there. Sorry, that's super sloppy. To reiterate, the force that pulls it down the ramp is mg sine theta. We multiply that by this change in x, which is 5 meters. And because those are lined up together, we get a positive value on it. Now, we can take a look at what that friction force has to offer us up as well. And that's pretty easy stuff too. The gravitational force has got 100 joules. So the friction force So check this out. The friction force would simply be negative 100 joules. So that would be our answer to C. Okay? Now, if the friction force wasn't the same? Like, let's talk about how this friction force would be different. Talk about how this friction force would be a little bit different if it wasn't constant speed. Okay? So this C is with constant speed. Let's try this. Let's try C this way. So the work by friction, in this case, would be this negative 33 number, ends up giving us negative 52, roughly, joules, I think, unless I'm crazy. Oh, wait a minute. I just, hang on a second. 0.3 times 4 times 9.8, 0.866 equals. I got calculator crazy, people. I got calculator crazy. I only gave half the answer. Because that's a 0.30. Sorry, I went bananas on my calculator. 5 times 9.8, 0.866 equals 33 times 0.3 equals, this is 10.2. Sorry. That's a little better. So look what we have here, okay? In this problem, we made an assumption that this was going at constant speed. This can't be going at constant speed, and here's why. This is 10.2 newtons. And then before, we calculated that force out as mg sine theta, which is 19.6. So let me say it again. This problem looked like it was going to be a constant speed problem. But the fact that they gave us 0.30 in there means they gave us a coefficient of friction which did not lead to constant velocity. So we had a discrepancy in the problem. Okay? That won't change the answer to A, and it won't change the answer to B,
And it didn't change our answer to C, but here's what we want to know for D. It says calculate the work done by all the forces in the X dimension. Okay.
We're going to calculate all the work done in the X dimension now. This is all we need. For D, work net for the X dimension means that we could take the difference in forces. So we need just as simple as this. So that would be what? 19.6 minus 10.2? This would be a net force of 9.4 newtons times 5. .47 Newton meters. Or joules. Look, I got ready to write joules. We'll just say Newton meters. There we are at the end of the day. 47 Newton meters. Here's what I like about this problem, ladies and gentlemen. What I like is that you have a free body diagram that you've got to deal with. You've got a net force equation that you have to deal with. And then look, we made an assumption that these were equal to 0. And what we're going to find out is that that assumption worked in the y dimension. That assumption did not end up working out for us in the x dimension. We would have to assume that is occurring right there. And let's be honest, work can cause accelerations. Net work can either cause no acceleration, or you can do net work and cause an acceleration. So that isn't so crazy. I just wanted to show you this problem and highlight it because it looks so easy sitting there on your checkpoint in the 1 position. But it actually is a little more challenging than you'd think. The answer key to this checkpoint is online. But here's the deal. I have no interest in you all. I have no interest in you guys going through this right now and solving them all out. That's something that we're going to do next week. So for right now, today, I'm just going to say that's it for the day. I'm thinking that's all I want to do with you all. And that took way too much time anyway. I'm sorry it took so long, but it was kind of a beefy problem. I want to do some reminders for some people out there based on this, and then I'm going to cut you guys loose. All right? Today's agenda, oops, I'm in the wrong place. Here we go. We had homework that was due today. Some of you have not uploaded your homework into the correct file yet. So what I'm looking for today is, look, we did energy problems and solved them. Instead of doing it, we did that for 2 days, right? So basically, your computer simulation is going to be due Saturday at midnight. A couple of you have turned it in. Nice job. Look, homework problem 7. Chapter 7, 1, 2, 3, 11, 15, and 21. Those were actually due before class today. But if you're hanging on to them right now, upload them. Turn them in, all right? Because that's what I'm looking for. A couple of you have forgotten to do the ed puzzle. The ed puzzle was due last night at midnight. It will still let you in to do it. So get into the ed puzzle and get the ed puzzle done. So there we go. We're done for today. Get these tasks done. This will tidy up the week. There is no
you do not have to do this checkpoint worksheet. That's not on the agenda anywhere. I just used it to solve a problem today. That's literally all I did. Okay, you guys are good. That's all there is. I'm letting you go. All right, you guys are amazing. I hope you guys have a great weekend. Go Steelers. They play on Sunday. But that's it. That's all I have for today. All right, thanks for playing, and thanks for solving some math problems with me.
Thank you.
You're
Thank
welcome. You guys are the best. I miss seeing you guys all the time. We'll see you later. Have a great one. You guys take it easy. Well, gee, I'm going to load that thing for you. Not even here.